Good afternoon, everyone. It's my great pleasure to introduce Dr. Shijia Pan, who is an assistant professor at the University of California, Merced. She received her bachelor's degree in computer science and technology from University of Science and Technology of China, and her PhD degree in electrical and computer engineering from Carnegie Mellon University. Her research interests include cyber physical systems and Internet of Things. She has published in both top-tier computer science, ACM and IEEE conferences, and high-impact civil engineering journals. She received Rising Stars in EECS Award, Nick G. Blahalkis Graduate Fellowship, Google Anita Berg Scholarship, and several Best Paper, Best Poster, and Best Presentation Awards from IEEE and ACM conferences. Thank you so much, Dr. Pan, for accepting our invitation. Please go ahead.
Thank you for the introduction. So hi, everyone. I'm Shijia, and I'd like to introduce my work on the cyber-physical system for device-free human sensing, human monitoring, where we try to utilize less resources, that's why we call it sense for less, by incorporating the physical knowledge from different domains. So people spend most of their lifetime indoors, and according to EPA, Americans spend 87% of their time indoors on average. And that's even before COVID. And now I bet we're spending even more time in the indoor environment. And as a result, various cyber-physical sensing systems has been designed to capture this human information to enable many different smart building applications. So when we say indoor human information, I really want to narrow down the scope for this talk because we have a lot of researchers been exploring human information acquisition at different scales. For example, on-body physiology information like EEG, ECG, to the in-home activity of daily living, which is what we are targeting, and even to city level traffic mobility information. So what my research focus on is at building or household level scale, where we want to know the identity, location, activity, and the physical condition, such as gait or heartbeat, this level of information. And it's usually what we call a context level or action level measurement. So there are, as we talked about before, there are various sensing modality has been explored. Of course, we're not the first one to do this, right? So there are many different modalities, and we've been categorizing them mainly fall into two categories, the device-based and the device-free systems. So the device-based system would usually rely on the user to carry a device with some specific sensors on it. And it could be a mobile phone, it could be a wearable, and sometimes recently there are a lot of new research on the earables where they target to acquire very fine-grained information from the on-ear sensing for the physiology level information. And on the other hand, for the device-free systems, where they often rely on a fixed sensor in the environment, in the infrastructure, for example, the vision, the surveillance camera, this type of devices, this type of sensing systems. We call it device-free because the person, the target, does not need to carry any devices, hence device-free. Other than vision, we see RF-based, the passive RF-based method, the light-based method. They rely on their measurement of the phenomenon that induced by human-environment interaction to enable the human information inference. So we focus on the device-free human sensing for the motivation of a lot of applications such as patient or elderly, long-term in-home monitoring. So why device-free is specific for them is because the target sometimes may not be able or even remember to wear or carry devices all the time. And furthermore, for many sensors that are able to acquire high resolution information, they're potentially power hungry, and the device-free infrastructure sensing are often easier to match such requirements for long-term continuous monitoring. So all this sounds really great for the target application, but do we have any challenges? In order to explore the challenge, I always like to start with an ideal setting, ideal scenario, where I assume we are super rich, that we have unlimited resources. So what if we have unlimited resources like sensors, storage, computing power, the labels, the data, we have all this, whatever we want, then things become so easy. There's no challenge there. But as you can see, it's probably really ridiculous if I want to monitor an elderly for their fall risk while they have to dodge the sensors I put on the floor every 1 meters. So the question we ask is, how can we acquire more human information through sensing with less resources? So the first challenge I would like to discuss here is, how can we reduce the sensor needed to acquire this indoor human information? So for in-home long-term person monitoring, it requires non-intrusive design, and the deployment would not, so that the deployment would not change the behavior of the target. And furthermore, for many emerging applications such as behavior profiling or mental health monitoring, fall risk estimation, fine-grained and continuous information is needed. So how can we do that while being non-intrusive, right? So how can we achieve this with very limited or even less sensors? So our answer to that is to use structures as sensors. The intuition is that we are actually causing physical vibrations all the time. When you walk on the floor, when you even sitting in your chair, you are causing physical vibrations. And these vibrations would travel far in solid. So if you put a sensor, say 10 meters or 5 meters away, they can still detect this vibration. And since we are indirectly inferring the information, that means we can achieve a non-intrusive information acquisition. So if you put a vibration sensor, if you turn the structure into part of your system as a vibration sensor, we'll be able to achieve long-term fine-grained and non-intrusive monitoring. So is this possible? We put a sensor to validate this idea. We put the sensor, a vibration sensor that's being used for civil engineering, structural health monitoring, earthquake monitoring. We just simply put it on the floor. Then, as you can see here, a pedestrian walks by. And here are on the left corner, we show the signal our sensor acquiring. The top one is a time domain signal, and the bottom one is a spectrogram. And you can see the red boxes are circling out what's being detected as when the footstep falls on the floor. So, okay, it sounds like we are able to capture human footstep signal with a vibration sensing. So we further look into what really happened when a footfall occurs on the floor, which is the heel strike would induce the surface of the structure to deform. Then when the heel is lifted, the surface would redeform, which induces a vibration. So this impulsive vibration signal induced by the impact is dominated by what we call Rayleigh lamp wave. And there are many specific properties of the relay lamp wave, which we study to further enhance the sensing system, which we will briefly introduce later. Then again, what do we mean by structure as sensors? Is that we are looking at people interacting with the structure all the time. And this structure could be floor, the structure could be the wall, and could be the bed frame, right? And we use a vibration sensor to acquire the structural vibrations signals. Then we characterize the signal, learn and model the signal that's been characterized, and then we'll get the human information. So the part where we utilize the understanding of the structure, such as we talk about the relay lamp wave, we studied its property, and then we utilize the property we learned to expand the system sensing ability so that we can allow accurate indoor human information inference. This is what we call structure as sensors. So let's take a look at a few examples of type of information we can acquire through this new sensing modality structure as sensors. We can do pedestrian identification. The intuition is that when people walk, when they the foot strike the floor, they actually strike the floor very differently because their walking pattern is different. For example, on the left-hand side, you can see person A, when he walks, his center of gravity is kept in the center with a less foot and floor angle, while person B, it looks more relaxed and leans back while she walks, and her foot and the floor angle looks larger. When we did this experiment, we actually joke about this to person. Guess which one is a PhD student? The person A is actually a PhD student where he rushed to his experiment all the time, while person B is a master student where we always joke that she walks with more relaxed gait because she knows when she will graduate. So because of all this gait difference, their footstep-induced vibration shows very different time and frequency domain characteristics. And as you can see in the center of the figure, where we show the time domain signal of these two persons' footstep-induced signal. And the slope is different, the shape of the waveform is different, which as a result, their frequency domain characteristics, like where the peaks frequency is and where the each peak's amplitude are very different. So imagine we extract all these features and throw it into a supervised learning a classifier. We can easily identify these two people when they walk by again. So we did the experiment with 10 people, and we for each footstep, we can achieve 90% accuracy. And if we consider multiple steps when they're walking by, we can even achieve 99% pedestrian identification accuracy. So that's what we can do. We can identify people now. How about location? When we have multiple sensors in the area and the footfall occur, this vibration signal would travel through the floor and arrive at a different sensor over different distance, hence over different time.
Shijia, can I ask a question?
Yes, yes, please.
In the previous slide, what was needed for you to do a larger scale test? So you did this analysis on 10 people. So if you wanted to do it on 50, 100 people, what was the what did you need and why you didn't do that in a larger scale? So it's interesting result, but I would like to know what is necessary in order to, what are the requirements to do that in a larger scale?
I see. So the reason we are targeting at approximately 10 people is because we are looking at, say, the in-home long-term monitoring, say elderly or just a smart home where you have a family approximately like 5 people-ish as a household. So that's why we didn't go for more people. Imagine you do this in a, say, office building where you have 50, 100, even more people, right? Intuitively, there will be more people who have more similar gait, like gait parameters, which might induce similar footstep, like floor vibration, and causing a lower classification accuracy if we just keep using this supervised learning model, right? But as we mentioned, we can extract a more detailed information to handle that when more test human subject would induce more confusion in the simple models. Does that make sense?
Yeah, thanks. Thank you.
Great. Great. So other than identification, we can do the localization when there are more sensors in the area. And the intuition is just like a lot of other devices that rely on multilateration, where we look at uh, how the signal propagates to different sensors over different time or distance to directly calculate the location of the source. So there are challenges, of course. A few challenges including the dispersion effect that's very special for the wave propagating in solid. Furthermore, because we are looking at a different structure, different material, we don't really know the wave velocity that these waves are propagating to. So which makes it quite challenging comparing to existing work on the, say, acoustic-based localization. So we developed this adaptive multilateration method that finds optimal velocity and the filter setting so that we can handle the unknown wave velocity and the dispersion effect altogether. So due to time limit, I'm not going to go into details for that, but a long story short, we were able to achieve a footstep level localization at a 0.34 meter average error, which is 6 times improvement if we do not use adaptive multilateration, but just use regular multilateration that's been working quite well on the acoustic signals. So we did deploy our system in a few different scenarios for different application. We put it in the nursing home where we're trying to acquire this type of information from the elderly to help understand their activity, their gait information, how well they walk. We put in the sleep lab to estimate the sleep stage based on the motion of the patient during their sleep. We further put in a pig farm where we try to detect the mother pig's ear behavior that might endanger the piglets. So in summary, we're doing the structure as sensors to reduce the number of sensors needed to acquire the human information. We did identification, localization. Based on localization, we turn any surface into a touch input, and we were able to track the sleep stage as well as the activity of different of people over different scenarios. So that sounds great, right? So now we can sense with less sensors. Problem solved. let's look at what's behind the scene. What really makes this structure as sensor happens. These are our good PhD students who are doing this super hard work that try to make this great ability to sense to happen. So this is really a large amount of time spent to configure the system in the first place. That's why the second challenge we're targeting is, can we have less configuration effort? Because this is just a one hallway, it takes 1 hour to deploy. And imagine we want to cover the entire campus or entire residential deployment for elderly or for people who do not have the domain knowledge about these sensors, right? But those gonna be very difficult. And furthermore, these sensors themselves, they need this configuration before they can work in all those scenarios, especially for systems that have multiple sensors that get collaboratively computing this human information. So how can we achieve less configuration efforts for all this cyber-physical or Internet of Things systems? So our answer is to enable the system to achieve automatic configuration themselves. And how can we do that is we are trying to use multimodal sensing signal via their shared context. The configuration we talked about here include but not limited to the device pairing, assigning or labeling the sensor information such as sensor location, etc. And our solutions through multimodal has an intuition that there will be various IoT devices with different modalities co-located as we envision where the future is going to go. And due to the difference of these multimodal systems, sensing systems, information acquisition nature, they often have a complementary information. Say one sensor can detect this information better, but less for the other. Despite these difference, they do have the shared context that they are observing at the same time. Say if multiple sensors are being installed in one room, all the events that's happening in this room will be detected. So we are trying to utilize the shared context for these co-located devices to achieve the auto configuration for them. So let's take a look at one configuration scenario. We're trying to achieve the secure pairing for co-located devices. So because IoT device hosts important human information, we always want these devices at home connect to a secure network. And with the number of devices that's been increasing, it makes it very label intensive if we just try to manually pair every device we got. On the other hand, these co-located devices have sensors that can capture events in the environment. So what is the invariant property across the observation of over all these sensors? So we take a look at all these different sensors when we do activities in the same environment where they are all co-located. We see, okay, for the vibration sensor and the microphone, they are detecting some shared events like knocking or door opening, closing, while the power meter and the microphone detects when the coffee machine is on. So you can see what's really shared here is the time when things are happening. So time is the invariant property across all these different modalities that we can utilize to achieve their information association. So these unequal signals that's captured by different sensors are converted to a shared space, which is time. And the time interval between events are then used to generate a fingerprint that can be further used to establish the key agreement, and eventually we can acquire the equal symmetric key for the secure pairing. And if we do this over time repeatedly, we'll eventually be able to get a really strong, really trustworthy pairing. So we compare the fingerprint similarity between these co-located legitimate devices, which we see they can achieve 94.9% similarity, while the malicious one that's been snooping outside can only reach 64.9% similarity. So this indicates that with the understanding of the co-located events, now we can make the configuration of the pairing, of the system pairing, easier. So let's go back to our structure as sensor modality in this aspect. And turns out not only we need pairing, we also need more information about the sensor so that it can work. So the system actually needs to know absolute sensor location to enable what we talked about earlier, that such as localization or activity recognition. And again, right now, all this absolute sensor location estimation is now manually input by the installers or experts, which are the grad students that's actually doing the work. So on the other hand, vision is a very well-developed sensing modality that can be co-located with other IoT devices. It could be maybe temporarily as a bootstrapping phase regarding the privacy concern, but everyone is aware that vision is quite well developed. So why don't we use the developed modality to help the developing one automatically configuring themselves, just like the structure as sensors we talked about. So the intuition is that the footstep location is a shared context between the camera and the vibrations sensing systems. So if a person walks by, both camera and the structure vibration sensor can sense the person and can also localize a person. A one-dimensional version of the vibration-based localization would work as simple as follows. When a person walks by a sensor, their footstep-induced signal energy would increase, then decrease, because when they approach and leave, the signal decay model would be very different for each footstep-induced signal. So we'll see this peak because the person approach and leave the sensor. And this peak would indicating the like where the person is closest to the sensor. So we call this pattern as a profile of the footsteps signal energy change. And this pattern can be profiled to relative locate the footstep to the sensor. But on the other hand, if we look at the camera can recognize a person's posture in the camera view, as we see before the skeleton detection. And if we have a camera in the environment, the camera can assign the absolute footstep location to the anchor point for every footstep. So if we associate this peak of footstep location detected by vibration sensor, that's relative for the vibration sensor, we associate this to the information we get from the vision, we'll be able to estimate the absolute sensor location from the corresponding footstep location captured by camera. So we're utilizing the camera to localize the vibration sensor through the human. There, of course, there are still challenges to this simple idea, because the pure data-driven approach would work very well on an ideal floor with simple wave distribution model. But in real life, there are a lot of structure elements such as a beam and partitions that would directly impact the signal characteristics. So for example, in this case, the signal energy profile will no longer, as shown in the curve, the orange curve here. Instead, we would observe a different profile when there are beams around. And if we still rely on the pure data-driven approach, we would end up with a wrong sensor location estimation. So what can we do? So turns out this type of beam effects has been very well studied in the structure and the mechanical engineering. And figures here shows a simple model for a floor slab of length L, where a force is applied on the point on the floor that is XF distance away from the beam, and the displacement of the point on the floor that is XS distance away from beam is calculated as below here in this equation. So again, I'm not going to go into details of this equation, but what it means that if we know with a known beam location, we can actually estimate the first step signal energy profile for a given sensor location. And with this insight, we can adapt our data-driven model to incorporate this knowledge to achieve the accurate sensor location estimation. And again, more information are in the paper. But long story short, we tested our system in the real world scenario, and we compared to the pure data-driven model as a baseline, which shows approximately 2 meters error in terms of sensor location estimation, while ours achieved the 7 centimeter estimation error when incorporating the physics model of the beam effect. So the take-away message here is that we are repurposing the sensing data for human-free device configuration by a multimodal physical context. So we published a few papers in terms of auto pairing as well as auto configuration for the less effort of the cyber-physical system configuration. So now we can easily deploy a system and make the building smarter. Sounds like we solved the problem, right? Not really. As we mentioned before, all these device-free systems are relying on the interaction between the human and the physical world to infer their information. That means the physical world, the complicated physical world, would impact your data distribution significantly. So if we rely on pure data-driven approach, we're going to need a very large amount of label to cover all the scenarios. If you think that's fine, it might be fine for you, but it might not be fine for the grandma here. So our third challenge is how can we sense or how can we learn from the sensing data with less data or less label data? The target problem is the data distribution change over different sensing conditions, and the label data for physical systems is always difficult to get. So our answer to that is to adapt the learning algorithm or the model guided by the physical information. We explored the environmental data distribution change, the target human data distribution change, and the data granularity change. We explore a little bit more, but for this talk, I'm gonna talk about the target data distribution change and how do we handle that. So let's go back to the pedestrian identification problem, where we say we tell you that the trace level classification over 10 people reached 99% accuracy. So because of this promising number, we got a little bit cocky, and we did a test that we call cookie test, where we ask this, again, the same 10 people to come back, and we tell them there's a free cookie at the end of the hallway. So they just went and get the cookie, and we're trying to find out who they are. And the trace level accuracy drops to 72%. What went wrong? We were wondering. They're just getting cookies, and it's completely ruined our system, right? So turns out the people's gaits change when they walk at a very different speeds. So when the steps of frequency change, as you can see, there are two examples here. When the person walks at a high footstep frequency, their ankle of the foot and the floor might be larger. Their step length might be larger, and that's all directly impact their gait, which directly impact the footstep signal. If we train with a high footstep frequency signal here, as shown on the top figure, and test on the low footstep frequency induced vibration signal, even from the same person, from the bottom figure, even we can see these signals shows very different time domain characteristics. So if we put the top one as training set and the bottom one as a testing set into a supervised learning model, of course we'll get low prediction accuracy. Even I wouldn't say they are the same signal. So a very simple solution for that is, let's just get data from all the walking speed. We did that, and the accuracy goes back to 98% accuracy. So that seems to be a very simple solution, which is as simple as asking your grandpa to walk in the hallway 1,000 times. And if you change other parameters, they'll have to walk more. So how can we make grandpa work less? We look into the physical relation of the data. So we actually ask the person 1 to walk at 7 different frequencies, where for each step frequency, or walking speed, we collect 35 step signals. And we put them together to cluster them based on their similarities. And we discovered that all these over 200 footstep induced vibration signal mainly fall into 3 clusters, where if we further look at their relation to the step frequency, we notice that the cluster 1 occurs more in the high walking speed. As you can see here on the right figure, the x-axis is step frequency and the y-axis is a cluster appearing percentage. The cluster 2 appears way more in the medium and low frequency comparing to the high frequency, while the cluster 3 only occurred when the person walks with a low step frequency, when the person walks really slow. So we further examined what happened in the cooking test. Turns out, when we collect the training set, the person was walking at their normal medium step frequency, while when they get the free cookies, free food, they somehow walk faster. And that results in we trained our system with more of the cluster 2 waveform, while when we tested in the uncontrolled cookie test, we actually tested on a cluster 1, more of the cluster 1 data distribution. So that's why we have a fairly low detection identification accuracy. But we do make an observation here that these clusters, the appearance percentage, their distribution is changing smoothly over the step frequency. So let's keep this observation in mind for now and get back to it later. Other than us, of course, their prior work tried to handle this data distribution shift problem. For example, the transductive transfer learning, where they take into account unlabeled data when modeling. So it solves the problem to a certain extent, where as long as the unlabeled data distribution has some similarity to your labeled data, it works quite well. So if we combine the prior observation, the data distribution changed smoothly with the footstep frequency, which is a measurable physical attributes. What can we do? Well, what can we learn from it? We actually can tell when does this transductive transfer learning works well. So given the labeled data distribution here, we would know the unlabeled data that's being marked in the circle here can be accurately predicted if we are only look at the part that's very with data distribution that's very close to the label data, meaning the first step that has step frequency that's very close to the labeled first steps data's step frequency. So with this observation, we propose iterative learning guided by physical attributes, where we first need to understand the relation between the physical attributes and the data distribution change. Then we handle similar data distribution change in each iteration. For example, here we select the unlabeled data that has similar similar step frequency to train first with labeled data. Then at the end of the iteration, we would expand the model by labeling the unlabeled data in this iteration that has high prediction confidence. So now we have unlabeled data that covers, now we have labeled data that covers a larger, a wider data distribution change. Then in the next iteration, the model would be able to handle the unlabeled data that has a larger data distribution change comparing to the original labeled data. So on and so forth, we did it iteratively and expand the model iteratively. Eventually, we are covering the whole distribution that's being collected. So the key here is that we are utilizing the physical attributes to control the iterative learning order. So that we can ensure in each iteration, we are getting the high learning accuracy. So we did our evaluation with, again, 10 people, where we collected their first step induced vibration over different walking speed. We put it as step frequency from low to high, and we only have the label data from the medium step frequency. So if we utilize a support vector machine, we utilize a supervised learning as a baseline, we can see when the data distribution are the same as a medium step frequency, they achieve quite high prediction accuracy, just like we showed before, 98% accuracy. But when the first step frequency are extremely low or high, the accuracy dropped so dramatically that it drops to 10%, which is almost random guess. So if we look at our iterative learning, where we control the learning order based on the measurable attributes, we actually achieved the 3 times higher or even up to 4 times higher identification accuracy on these extreme walking speeds. So the takeaway message here is that the transfer learning guided by the physical attributes that can be measured can be used to handle the target condition variance. So in terms of the physical informed learning adaptation, we did some work on the physical guided transfer learning to handle the structure difference, the environmental difference, and the iterative learning guided by the physical attributes that we talked about is used to handle the human variance. And we recently also explored how can we do cross-granularity semi-supervised learning, where we can utilize a very small amount of fine-grained label data and the easy to access coarse-grained label data to acquire fine-grained activity recognition with very limited data. And in conclusion, from the system perspective, we explored how can we sense better, where we utilize the structure as sensors to reduce the number of sensors needed to understand what's going on in the environment, what are the human informations. We explored how can we utilize multimodal IoT to automatically configure the system so that we can reduce the system configuration effort. Then from the data perspective, we explored how can we make the system learn better, where we study the data distribution change and its physical costs to improve the classification accuracy with very limited initial label data. So that'll be end of the talk. Please let me know if you guys have any questions.
Thank you, Shijia. It was a very interesting talk and exciting research topic.